In this lecture, we want to begin talking about what we call measures of central tendency. And what this lecture will introduce will be the first numerical measures to summarizing a data set. Okay, so what are measures of central tendency? So here what we're going to do is we're going to look at three different concepts that describe what a typical element of a data set is. Now there's the mean, which you probably have heard of. What this is synonymous with is the average of a data set. You've heard of the median before, right? This is the middle value of a data set. And then we're going to introduce something called the mode, and this is the most observed. All right, so we have the mean, median, mode, or the three M's for the measures of central tendency. Okay, so first off, definition to start with the mean. Now in this class we have two different types of means that we're going to define. One is called a population mean, and one is called a sample mean. Okay, this population mean is a parameter. If you remember, a parameter is a value that's calculated from a population, and the sample mean is what we call a statistic because it's the value calculated from a sample. Okay, and now you've all probably taken an average before. Like if you wanted to calculate, what would the average test score among 10 students, right? You just add up the 10 values there were and divide by 10. But what I want to talk here really mostly about here is the notation, because the notation of these values, the difference between a population mean and a sample mean, is incredibly important in this class. All right, so it goes like this. If x sub 1, x sub 2, all the way to x sub capital N. Now remember what capital N stands for? Capital N stands for the population size. Okay, are the n observations of a variable from a population, then the population mean is given by this Greek letter, and this is the Greek letter mu. And it's just given by the following. Well, the population mean, you take the first value, you add it to the second value, you keep adding up all the way to the last value, and then you just divide by how many there are. That's it. In shorthand notation, we use this sign here. Okay, this is the summation sign in mathematics. So this is just saying sum up all the individual x values, that's what this x sub I stands for, and divide by capital N. That's it. Now the next example here, if x sub 1, comma, x sub 2, comma, x sub lowercase n. Now are the n observations, so this lowercase n, just recall, this is the sample size. So the subtle difference between capital N and lowercase n. Are the n observations of a variable from a sample? Then the sample mean is given by this notation here. This we just call x bar. All right, so x actually with the bar above it is literally just called x bar. And this is given by, it's the same basic formula here. X bar is equal to, you take the first value of your sample, you add it to the second value of your sample, you keep adding, you add up all the values of the sample, and then you just divide by how many there are. So in shorthand notation, this is just the sum of the individual x values divided by how many there are. And it's a very, very straightforward process here. All right, so let me just give you an example. Okay, so here's an example of a population mean. So there's 3 countries in North America, right? So capital N is equal to 3, and their land areas are the following. Here's the land area of Canada, here's the land area of Mexico, here's the land area of the United States in kilometers squared. What is the average land area? This would be a parameter. Okay, because we have all the values in the population here. Okay, it's not a sample, it's not a subset of the population, so it gets this notation mu. And you're just going to add up all their values, divide by how many there are, and we would say that the population mean average land area here is basically 6.7 million kilometers squared. All right, well, how about the sample mean? Suppose you just asked 10 people how many hours of TV they watched last night. Here are the responses in hours. Okay. 1 hour, 2 hour, zero point 0.5 hours is half an hour, 0 hours, 4 hours, all the way through. What does the sample mean here? So this is not a parameter. This is going to be a statistic because it comes from a sample. Right? More than 10 people watched television last night. So this set of 10 observations is obviously a sample. So it gets the X bar notation. And again, just, how do you take an average? You add up all the values and you divide by how many there are. So here there were 10. So if you add up all the values, you get 14 divided by 10. So it looks like the average of these 10 people, they watched for 1.4 hours of TV last night. Okay, let's talk now about the median of a data set. Okay, so this looks at the midpoint of data when they are sorted from highest to lowest, or it doesn't matter. Or you can do lowest to highest. Okay, that's generally actually how I will do it. So I use an algorithm method that I'm going to talk about in here. I use the n+1 divided by 2 position to find the median. Okay, so there's two different cases here. If the number of observations is odd, it's very, very straightforward. If the number of observations is even in a data set, it's just actually an extra step. All right, so if the number of observations is odd, then the median is the data value that is exactly in the middle of the data set. That is, the median is the observation that falls in what we call the n+1 divided by 2 position. Okay, so you just take how many there are, you add 1 to it, you divide by 2, you go to that position in the data set, and that's where the median will be. Okay, if the number of observations is even, then the median is the mean of the 2 middle observations of the data set. Okay, so this is a little weird. To find the median, you have to take the average of the 2 middle data values. Okay, so that is, the median is the mean of the data value on either side of the observation that lies in the n+1 divided by 2 position. Okay, I'll do an example of both, where one you have odd and one where you have an even number of data values. Now, I just want to note, going back, the different notation here for the mean of mu or x bar is incredibly important. For the median, however, we don't have a special designate for it. Okay, right now it'll eventually be called the second quartile. We'll get to that in a little bit, but for now we can just write it as median. There is no specific distinction between the population median and the sample median. Okay, so let's find the median of this example here. So Robert hits 11 golf balls at Grisby driving range, okay, and the recorded distance of his drive measured in yards are given below. Find the median distance of the drives. Okay, so it looks like it had a drive that only went 50 yards up to a drive that went 140 yards. So I use this n+1 divided by 2 position. Well, n is the sample size. So this is 11 plus 1 divided by 2. This is 12 divided by 2. What I'm saying here is the median is in position 6. So in ordered data, this is position 1, 2, 3, 4, 5. Here is position 6. So what I'm claiming to you then is that the median of this data set is the value 85. Okay? And you can see that. You can just quick look at this. You can kind of eyeball the data set, and you can see that the value 85 falls right in the middle there. Okay, so I have it a little bit cleaner on the next slide here. You can see right here, that's the median, falls right in the middle. All right, so I did it by ordered data, n+1 divided by 2. Well, 11 plus 1 divided by 2 got me 12. Divided by 2 gets me position 6. Okay, but now what happens when the number of observations is even? It's a little bit more tricky. Okay, so instead, suppose he had 12 golf balls at Grisby driving range, okay? The recorded distance of his drives are given below again. Find the median distance here. Okay, so you're still going to use this n+1 divided by 2 position. Well, here, now my n is 12. So this is 12 plus 1 divided by 2, which is 13 divided by 2, which means the median occurs in position 6.5. So that's weird. So here's position 1, 2, 3, 4, 5. Here's position 6. Here's position 7. So what that means is the median falls between these two values. So what we do now, once we recognize that, is we say the median is equal to the mean of these two values. So 85 plus 95 divided by 2. Okay, because there's only two values, that's how we find the average of that. So this is 180 divided by 2. The median of this data set would then be 90. Okay, so the only difference here is when there's an odd number, you go right to the position in the data set, piece of cake. When it's an even number, you have to take the mean of the two values for which side the median falls between. And you can see here, just cleaned up a little bit, it's a little bit easier to see it just like this. Okay, so this is just one way to do it by hand. I'm going to eventually show you in a follow-up lecture how to do this with a graphing calculator, which will be good. Okay, the mode. So the mode's really easy. There's no special formula to this, and there is no difference between the population and sample. So here, mode is just the most observed. Okay. So here's an example. Here are 20 opinions of Hillwood Cafe. 3 people said it was excellent, 6 said it was fair, or 6 said it was good, 7 said it was fair, and 4 said it was poor. So it looks like the mode here would be the value fair. You can also do it in a data set like this. Suppose you have numbers. You have a data set that looks like this. You'd look through the data set and you'd say, oh, okay, the number 4 here is the mode. All right, let's go on now and talk. The mean median mode should definitely be pretty straightforward. So let's go on now and talk about something called the weighted mean. Okay, and the weighted mean occurs when you have some observation that you wish to place more importance on than others. Okay, so some values are more important for whatever reason. And I have 2 examples in the slides here that will help illustrate this. So to do this, when one value is more important, they require what's called a weighting variable, okay, that indicates the importance to place on a given observation. Okay, so think about the weighting variable as how much you want to weight how important it is. So we denote the original variable by x sub I, and then its corresponding weighting variable we denote by w sub I. All right, so the corresponding weight. All right, so these values have to correspond to each other. Okay, why would we need this? Well, let me show you first an example talking about life expectancy. Okay, or excuse me, let me give you the formula first for this, obviously, sorry. All right, so the formula for the weighted mean is following. We're just going to denote it as x bar w, and I'm going to change it up a little bit here. You notice what you do first is I take the first weight and multiply it by the original value of the first value. So I'm going to write it even as x1 times w1, because products work the same. A times b is the same as b times c. And then you would add to it. You'd go to the second value in your data set, and you'd multiply that by its corresponding weight. And you'd keep going. You'd go through all the values in the data set, multiplying the original value by its corresponding weight. And this is really important. You do not divide by how many observations there are. You divide then by the sum of the weights. Okay? So we denote this in shorthand notation here. It's the sum of each weighting variable times the original variable, x sub I, or original variable times its weight, doesn't matter which way you do it, divided by the sum of the weights. Okay? All right, so how would you use this? Let me give you an example. All right, suppose I have this group of northern African countries, okay? Algeria, Egypt, Libya, Morocco, Nigeria, Sudan, and Tunisia, okay? And what you see here is you have the life expectancy in each of these countries, okay? So this data was pulled from the CIA fact book, so this isn't made up, okay? And if you look here, it looks like Libya has the highest life expectancy and Nigeria has the lowest life expectancy. Okay? Okay. Living to 73 is not too bad. Living to 41, that's tough. All right, if you were to take the average here, okay, the average of all these 1, 2, 3, 4, 5, 6, 7 life expectancies, you would say the average life expectancy in these northern African countries is 63.14 years of age. All right, but let me give you another piece of information here, okay, and why you might see we need to use a straight mean is not a great way to do this, and why we might need a weighted mean. If I give you the population of each of these, look at this. Libya, which we said had the highest life expectancy, only 5 million people live there. But Nigeria, which had the lowest life expectancy, 126 million people live there. Okay, so counting the value Libya the same as Nigeria is completely unfair. Okay, because look at this. Basically 25 times as many people live in Nigeria. So what we want to do is we want to place more importance on the value in Nigeria. Okay, so how do we do that? Well, one thing you don't do with the weights is you don't say, let me weight this one 1, this one 2, this one 3. No, you don't do that. So you have to find some other value of significance to weight it by. And we were interested in life expectancy. So that's going to be my original value, x sub I. That leaves this, the population, is what we want to weight it by. Okay? What we're saying here is we want to weight Libya with a value of 5, and we want to rate Nigeria with a value of 126. So it places, just by weighting it more, it places more importance on this one. Okay. So here, recall this was our original value. This was our weighting variable. And the formula was x bar weighted was the sum of each x value times its weights divided by the sum of the weights. Well, here I'm going to take this value and multiply it by its weight, and you get this. You're going to take this value, multiply it by its weight, and you get this, and so on. I'm going to keep going across here. All right, so then up here, to use our formula, you're going to have to sum each x value times its corresponding weights. Well, you need to sum all these values here. And when you do, you get 16,627. Now, you can't divide this by 7. You divide this by 7, you'd say that the life expectancy is over 2,000 years. No. That's why you divide by the sum of the weights. So you sum these, you get 302. And the more accurate description of life expectancy here, when you account for the population of each country, is 55.05 years. So you can see here, just a straight value doesn't take into account how large each country is in terms of population. So we want to put in this extra weighting variable here. So actually, an arithmetic mean is the same thing as a weighted mean. It's just every value has a weight of 1. All right, let's do one more example of weighted mean, okay? And this is your GPA example here, and I'm going to write this one out. It's not in the slides here. So if you ever looked at your grade report at the end of the semester, you get a grade point average. And what they don't do is they don't do just a straight mean, okay? They give you actually a weighted mean. So your GPA is a weighted mean, believe it or not. All right, so let's pick a student. So you have this student, and we'll call the student Matt. And let me tell you the classes that this student is taking. Okay? So the student is taking a stats class. That's pretty good. A calculus class, an English class, an economics class, and they're taking a running class, okay? And let me give you the grade that they got in each of these. Okay, the student obviously got an A in stats. They got an A in calculus. They got a C in English. They got a B in economics. And let's say they got a D in running. They weren't very fast. Okay. Next thing I'm going to do is I'm going to trade these grades to a number on a 4-point scale. So an A is worth 4, a C is worth 2, a 3 is worth 3, and a D is worth 1. If you just take the regular mean of this and just add these up, 4, 8, 10, 13, 14, the student was taking 5 classes, we'd say their GPA is a 2.8, okay? But that's not correct. That's not how they really do a GPA, right? I mean, if you think about it, stats and calculus are way more important than the running class. Okay, so what did they weight your grades by? They actually do it by the credits of each class. So stats is a 4-credit class, calculus is a 4-credit class, English is a 3-credit, economics is a 3-credit, and running is a 1-credit. So this was our original variable, x sub I, and we're going to weight it by the credits. So if you remember, our formula was the following. X bar weighted was the sum of the x values times their weights divided by the sum of the weights. So I'm going to put a little column here called xi times wi. And what I'm going to do is I'm going to multiply each x value by its weight. So 4 times 4 gets me 16. Again, 16. 2 times 3 gets me 6. 3 times 3 gets me 9. And 1 times 1 gets me 1. So look here. The next thing, the numerator here, I'm going to have to sum up this column here. Sum up each x value times its weights. So if you sum this up, okay, you would get 16 and 16 is 32, 38, 47. You would get 48 here. And you have to divide now, not by the 5 classes, by the sum of the weights, by the credits the student is taking. So 4, 8, 11, 14, and then 1. Student's taking 15 credits. So you would take 48 divided by 15, and the student GPA correctly would be a 3.2. So this is another example of the weighted mean, right? And I think it makes sense that we want to weight the stats and economics, stats calculus class a lot more than the running class. All right, I hope this helped as a quick introduction to your measures of central tendency.